Hello, welcome to Lecture 11 of Quantum Computer Systems. Today we are going to talk about the topic of classical simulations of quantum circuits. And in particular, this is the outline. First, we're going to introduce two different definitions of classical simulations, namely strong and weak simulation of quantum circuits. And then we're going to talk about three different approaches and analyze their trade-offs in terms of runtime and memory. So let's get started. Well, when we talk about classical simulations of quantum circuits, we're given a quantum circuit U of size n, and here size means the number of gates typically, and sometimes that also referred to as the depth of the circuit. And this number n is typically a polynomial in terms of little n, which is the number of qubits in this quantum circuit. So before we talk about what happens when we simulate a quantum circuit, let's review what really happens on an ideal quantum computer. The transformation that we want to accomplish starts from a tensor product of n qubits in the initial state 0. And after the transformation of U on my initial 0 state, I arrive at a quantum state psi. As I drawing here, we have the 0 state. After the transformation U, we arrive at some quantum state psi. And typically, a quantum algorithm would involve the last step of measurement on some or all of the qubits. After performing the measurement, we obtain a measurement outcome, which is a binary string of length n. Let's call that z. The probability of obtaining z for this quantum circuit u, so p sub u of z, is a distribution following the Born's rule, as we talked about in earlier lectures. So in order to mimic this random measurement outcome of the quantum circuit, we now have two different simulation definitions. First one is called the strong simulation. Given one of these binary string zi from a subset of output string of interest. This could be a subset of 0, 1 binary string of length n. We want to compute the probability of obtaining this output string z sub I or z sub I from this target output strings with high accuracy using a classical computer. So again, the goal is to compute this. Now the second definition is what we call the weak simulation. The goal of weak simulation is that we want to sample once from the distribution P sub u using a classical computer. Now this time, instead of calculating all the amplitudes or the probability values associated with each measurement output string, we just want one sample at a time according to the distribution P sub u. Now remember, what quantum computer does is closer to the definition of weak simulation. Every time we perform a measurement, it gives us one sample, one binary string of length n, according to a probability distribution described by the Born's rule. And here in weak simulation, a classical computer will mimic exactly this behavior, give you one sample at a time. Now, there are several remarks I want to make about the similarities and differences of strong and weak simulations. First of all, strong and weak simulations are fundamentally different notions. In particular, we can find circuits that are trivial when we want to simulate it weakly, but it could be Sharpie complete, Sharpie hard when we want to simulate strongly. And second, strong simulation implies weak simulation, but not the other way around. That's because if all the probabilities are calculated in strong simulation, then we can sample from the known probability distribution. But if you have an algorithm that can sample once efficiently from the distribution, but there are exponentially many probability values, it is not immediately clear how to recover all the amplitude or probability values with accuracy. Now, third, a weak simulation is closer to, as I said, quantum computer does this, in particular sample once from the distribution. So strong simulation may be too strong when we are studying the limit of classical simulation. But in today's lecture, the approaches that we're going to talk about fall into strong simulations. And finally, sometimes efficient simulation for a restricted class of quantum circuits, namely non-universal quantum circuits, can also be useful. Okay, now the first classical simulation strategy we're going to talk about is the most natural one. We have been doing this when we analyze quantum circuits. This is called the state vector simulation. Now again, the problem that we're given is that we start with n qubits, and they're all in the zero state. So we begin with 0 tensor n as the initial state. And now the quantum circuit consists of a series of unitary transformations. Here I'm writing them as m steps. So after the first step, we arrive at a quantum state psi1, that is u1 times 0. Then after u2, we arrive at psi2, and etc. until we reach the final quantum state psi sub m, which is um dot dot u2 u1 on our initial state 0. So the most naive way to simulate this process is to compute this quantum state psi I at each stage by multiplying the matrix of the unitary transformation u sub I sequentially on our quantum state. So at every step, you have psi sub I equals u sub I times psi sub I minus 1. Now remember, this quantum state psi is a vector of dimension 2 to the n, where n is the number of qubits. And because you are keeping track of the quantum state vector at each stage, you have to write this vector down, which leads to exponential memory cost, namely O of 2 to the n. And if we look at the runtime of this algorithm, you'll see it's also exponential in the number of qubits, because for every stage I, you'll need to perform this matrix and vector multiplication, both of which are of exponential size. And you're doing this for m step. So this algorithm gives you a runtime cost of O of m times 2 to the n. But can we do better than this? Well, are there special cases where the memory cost and the runtime cost can be lower? Let's take a look at an extreme example. And the idea is to look into this locality of quantum circuits. And what do I mean by locality? Well, I mean two things. First, the information is local, namely data are unentangled, which means the states at every stage of the quantum circuits is just a product state. So for each psi I, we can write the quantum state as tensor product of n local states. So here, each q sub I is, say, 1 qubit. So alpha 0 plus beta 1. In order for this quantum state to stay in product state, the operations in the quantum circuit needs to be local as well. So another constraint is that gates act on single qubits. So we can write down the unitary transformation at each stage I as a tensor product, where unitary transformation U acts only on a single qubit. Then if this is the case, the memory cost for this algorithm is that we only need to write down a quantum state in a product state form. The memory cost is going to be significantly reduced, and a product state has only 2n amplitudes instead of 2 to the n. And the runtime of this algorithm is also significantly reduced because we only need to update the local bit of the amplitude per gate, which means that for this algorithm, the memory cost is linear in the number of qubits, and the runtime is linear in the number of gates. When we have an efficient classical simulation algorithm that mimic the behavior of this quantum circuit, this means that this quantum circuit does not have an advantage in terms of the memory or runtime complexity. So this is why we say that entanglement, which this quantum circuit doesn't have, is a key source of quantum computing advantage. But I also want to point out that this entanglement is not a sufficient source of quantum computing advantage. It can be shown that there exist some quantum circuits with really high degree of entanglement, but we can still simulate them efficiently. One example of such quantum circuit is called the Clifford circuits, and the stabilizer formalism algorithm is an efficient way to simulate all Clifford circuits. Okay, now let's think about how to improve our simulation algorithms. First, let's think about memory improvements. So in this earlier state vector simulation, we always write down the quantum state as a vector of exponential size. Do we have to do that? Well, not really. And this is called the Feynman path simulation. Now, earlier in this lecture, we have used this Feynman path sum technique to analyze interference of computational paths. Now, let's take a look at how we can use the same picture to perform simulation, in particular to calculate the amplitude for an output string. So in this Feynman path diagram, we write down the possible transitions from the input string 0 to the output string x. So for a quantum circuit of m steps, we have m transitions from the input to the output. And the coefficients on each transition, or namely each edge of this diagram. For example, here I'm highlighting one of the edge in red. The coefficients on this edge is given by the input string A and the output string B, as well as the transition example here U2. So this edge has an amplitude of A, U, B. Now suppose for shorthand, let's call the function FBI as the amplitude of output string B after I steps of transformation. which means the final value that we want to compute here is the function fxm, so the amplitude for output x after m steps of transition or transformation. Now, if we look at the final output x, we can use this recursive picture that fxm is given by, for example, in this picture, 4 different computational paths to get to the output x. So it's a summation of all the possible paths b. Let's call this possible path b, where each path has a coefficient given by each edge. And this edge is a transition from b to x via unitary transformation u sub n. And if we look at one of the output b, the overall amplitude for b is given by the function f bm minus 1. And to include all possible paths to the output x, we can enumerate all possible b. In this case is a m-bit binary string. Okay, so if we have this picture in mind, then we don't really need to write down all the amplitudes. All we need to do is to perform the computation, use this recursive call. So let's take a look at the memory cost of this algorithm. First of all, at each recursive call, you need to write down the binary string b to indicate which input or output binary string are you considering here. So of course, you need O of n bits to specify the coefficients b and x. Well, you also need to keep track of the recursive call stack. Because you have m recursive levels, the size of the call stack is O of m. So overall, the memory cost is about n plus m. Okay, so for runtime, let's take a look at an example where if at every stage u sub I is a 2-qubit gate, so the size of this unitary matrix is 4 by 4, then we really have 4 branches for each b. And for the m recursive levels, overall, we'll need 4 to the m cost in runtime. And because 1 and 2 qubit gates are universal, we can consider only 2 qubit gates without loss of generality. Of course, the assumption is that the quantum circuit has m steps and each step has only a 2 qubit gate. Okay, so this Feynman path simulation technique is memory friendly, but the catch here is that we need to pay extra runtime cost. Okay, now how do we improve the runtime of the simulation algorithms? So far, the methods that we talked about are mostly ignorant of the structure of the circuit. For example, if your quantum circuit has m steps, and each step contains some quantum gates, in this particular example, U1 is really a single qubit unitary U tensored with identity on all the other qubits. If you look at this matrix, it's really sparse. And if every time you will need to constructing this sparse matrix of size 2 to the n times 2 to the n, it seems like you're doing a lot of redundant work. So how do we identify internal structures or locality structure in a quantum circuit? This is called the tensor network simulation technique. It essentially addresses the question, what if a circuit has sparsity in the unitary transformation? The key idea is instead of cutting the quantum circuit into steps where each step is given by a huge sparse matrix, we combine quantum circuits strategically. In particular, multiplying the quantum gates in this group together first can typically avoid doing the tensor product up to size 2 to the n times 2 to the n for every gate. It turns out that if you can do this grouping strategically, you can sometimes avoid doing redundant work of multiplying sparse matrices. The general technique to identify such strategy is to map the quantum circuits to a tensor network. Here, tensors are just a high-dimensional matrix, a convenient graphical representation of a quantum circuit. So a 1 or 2 qubit gates can be these tensors or nodes in this graph. Now here, grouping of quantum gates or multiplying the unitary matrices are generalized to contraction of tensors. So with this graphical representation, we can discover good strategies for combining gates by analyzing these graphs. So that's a very brief introduction to some of the common classical simulations of quantum circuits. Now we have introduced techniques from state vector simulation where we keep track of the quantum state at different stages of the quantum circuit, to Feynman path simulations where we do not need to write down all the amplitudes of the quantum states at different stages and trade off memory with runtime. And finally, to tensor network simulation, where we explore the locality structure of quantum circuits to avoid redundant work in multiplying sparse matrices.